If you add water across a triple bond in an anti-Markovnikov fashion, what you end up making is the aldehyde, and this mechanism is going to walk through that. So dicyamylborane, you want to think of always drawing out the Lewis structure for any reagent that you're going to use, involves two of these relatively large bulky groups bound. But for all intents and purposes, that doesn't matter. What does matter is that you're going to have two large things sticking out into empty space when you start this mechanism with the relatively small hydrogen over the triple bond and on the internal side. And so then when you draw the mechanistic work that leads to the next intermediate, you are organizing this transition state via size. So the outcome is that you have now added a hydrogen and a boron from the same side of triple bond to give you this double bond. And that's where we sit after the first step. So then the second step does the oxidation, and I'm going to skip that mechanism. As far as you're concerned, magic happens. This is a black box reaction, and you can think of it as jumping ahead straight to oxygen bound instead of boron. I don't care that you understand what's happening along the way until you get there. But once you're there, then you have an enol, and this is nothing more than a simple keto-enol tautomerization. Again, this is an enol. I will highlight that when you're doing the oxidative steps, you're doing it under basic conditions, which means that what we have around nearby is going to be some base, and in this case, almost certainly hydroxide. So I should always draw out whatever reagents I'm going to use in Lewis structure form, which means that I have a OH bond drawn like that. So the way this mechanism starts to convert is the base comes in, deprotonates, which causes those electrons to go onto the oxygen. That is your more stable intermediate, resonance structure I should say. But when you have the nearby water, because that's the solvent, you will pick up the proton from the other side. Rather than the oxygen picking up the proton to go back to where you came from, instead what happens is that the carbon serves as the base, regenerating the hydroxide, and the oxygen that's minus provides the electrons that allows this whole process to go. So this final step then leads to the aldehyde in a single step. When you're doing addition of water to a triple bond with a borane, what happens is a normal addition via the smallest possible intermediate. You want the H over the internal side, you want the larger borane over the smaller side. You deliver B and H from the same side to arrive at this material where the hydrogen and boron were delivered cis to each other. This is just left over. Oxidation of the boron leads to the oxygen material. I have shown this as the final product. It may just end up as O- at one point. Either way, deprotonation happens. You end up with this O- species eventually, and then when this picks up a proton, if it does through the carbon, you end up with the aldehyde. This again is a enol tautomerizing to its keto form. In this case, it's an enol going to an aldehyde. But the process of tautomerization, which is what this is still called keto-enol tautomerization for some reason. If there's a single message to take away, it's that when you add water across the triple bond, you end up with a carbonyl of some variety. Carbon-oxygen double bond. That's the final product.